Okay, another way to prove this result, and written everything out pretty much that follows immediately from what we looked at earlier. Again, we break down the expression for the Laplace transform of our periodic function, and it's equal, of course, as it was, to integral from 0 to t f of t e to the negative ts dt, plus the integral from t to infinity of the same thing. Now that's just what we did before, but I want to take this integral from 0 to infinity and write something that's fairly obvious. Okay, so we start with our integral from 0 to t, and then our integral from t to 2t, and then our integral from 2t to 3t, and we can continue doing that forever. Now, of course, these are just the integrals over the first, second, third, and so forth periods, subsequent periods. We can do the same thing we did with translation in this integral. That is, well, I haven't done the translation, so let's go ahead and say the integral from t to 2t can be written as the integral of f of t plus big T times e to the negative capital T plus little t times s dt, just replacing t by t plus capital T. In other words, translating this integral now to the integral from 0 to infinity. So we just do a horizontal translation of the integral in the second period. We just pull it over so that it's an integral from 0 to big T. Okay? And then we do the same with this integral. Now, we have to shift this over to get it to be an integral from 0 to t. We have to shift it over 2t units. So we do the horizontal translation, replace f of t by f of t plus 2 capital T. And same thing here. Replace both of these t's by t plus 2 capital T. And now we have integral from 0 to t. So what's this tell us? And then, of course, we can continue this forever. We've established enough pattern here that now we can write this as the integral from 0 to t, capital T f of t, e to the negative ts dt, plus what? Well, we can express e to the negative capital T plus t times s as e to the negative capital Ts times e to the negative little ts, and that e to the capital Ts, just as before, factors out. Also, f of t plus capital T is just equal to f of t and it's e to the negative capital Ts. Okay? And that's exactly what we did before with the integral from t to infinity, except now it's just the integral from 0, from t to 2t, which transforms this way. Okay? So then, same thing is going to happen here. F of t plus 2t is still equal to just f of t, function being periodic with period t. So I can replace this with f of t. I'll have my e to the negative ts here. And I'll have e to the negative 2 ts here, because I have a 2ts with a negative sign. And the pattern should now be clear. Now the point is that I have the integral from 0 to t of f of t e to the negative ts dt here, 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 and in every subsequent term. So that's going to be the integral from 0 to capital T of f of t e to the negative ts dt multiplied by 1 plus e to the negative ts plus e to the negative 2ts and so forth. And I'm running out of room here. This is just 1 plus, well, okay, I'm going to write this now as 1 plus r squared, where r is e to the negative ts. R squared would be e to the negative ts quantity squared, which would be e to the negative 2ts. And now I'm out of room. But now this is a geometric series. E to the negative ts is less than 1, so it's a geometric series on r with r less than 1, which is going to converge. So I can still write this here. Again, getting fairly close to being out of room here, but we can still see this. Okay, so this is 1 over 1 minus r, and if you don't understand geometric series, review it. Sometimes it gets skipped in the curriculum. I certainly hope that by the time you've been through 2 semesters or more of calculus, you understand a little bit about geometric series and you've encountered it. So it might just be that you have to review if you don't remember. And that's times the integral from 0 to t of f of t e to the negative ts dt and what's r? R is equal to e to the negative capital Ts so there's again your 1 over 1 minus e to the capital Ts times this, and that's going to match this. And that's another proof. And it's a proof that makes you think about what's happening on each subsequent interval. If you combine that with the geometric picture that we saw preceding, you get a pretty good idea of how this comes about from a couple of different perspectives. Now the text doesn't do the geometric, it doesn't do this, it does the more straightforward but less informative proof that you get from the straightforward breakdown of these 2 expressions.